This is a demo video for Lab 7, and this part is for the simulation for the GPU part. And first, as the instruction said, we need to build some module such as PC counter and other module. And so basically our idea is just use a 5-stage pipeline architecture and add a tensor unit into EX stage, and we use almost the same instruction type with about same type of CPU in Lab 5 or in Lab 6. So let's look at this module. The first one is PC, and in this part we make these two, PC plus 4 and the PC next. PC plus 4 is the current PC value plus 4, and the PC next need to take a look and find out the current instruction. If the instruction is jump or branch, we need to change our PC value to the target. And the instruction memory, we need to build some instruction in this memory. So first we store some value in here. In the data memory, and we need to use the lower instruction. And so as the instruction said, we need to divide our 64-bit data into 4 parts, and each part is 16-bit. So the first data stored in the data memory is this 4, and so we can see this is our data. So now we use the lower data to bring it to the register field in 1, 2, 3, 4, 5, 6 register in the register field. And of course we need to have some knob, because there's some hazard. And then we need to test the bit flow 16, and this is for the addition, and this is for the multiplication. And we need to store the result value to the register 7, and the value is from the number 1 and the number 2 register. and you can see this 8 value is what we need to multiply and add. So these two instructions is used to test the before 16 add and mode, and we need to have a ReLU active function, and the result is stored in number 5 register, and the value is from number 1 here. So the target result is 1 and 0 and 2 and 0.5, because -1 is cannot pass the ReLU active function. And also we need to insert some knob. And this is same. We just need to try some different value to prove that our code is don't have some small problem. So this is some extreme value. So the target is this for result should be all 0. And also this is for add and the mode. We can see the value here. And then we need to store some value, some result value to the main memory. And this part is almost the same as the 5-stage pipeline CPU. So I think the different lab 7 from lab 6 is we add the bfloat 16 and we add tensor unit, so we can perform a ReLU active function. And this is the register file. This is the same as lab 6. We read to address and output to data. And this is the memory. So when everything is in the beginning, we use the initial block to make sure the data is stored in data memory, and this part is almost the same as lab 6. Of course, we divide 64-bit data into 4 parts, and also we can do some bfloat 16. So nothing special here. And this is the pipeline register. So basically, it's only store some value and output when we have a positive edge of clock. And this is the ID stage. So we can find out that our instruction divide to this part, because if we divide our instruction into this part, it will be cost less resources. And we can see that in here we have some operation. For example, this is for the add and this is for the subtract, and this 2 is for the bfloat 16 add and mod, and this is for the value. And this operation is based on 16 bit data. And in this part, we can see that if we have the function the same as 0, now we can see that we need to perform this operation. And in lab 7, we didn't test the jump and the branch, but we keep it to make sure in the future we can use it. And this is the register, nothing very special. And this part is more important because we divide our data into 4 parts. And if we have add, so this is not a bfloat 16, this is a int. So we just use a simple add in here, and this is same. We use a simple subtract and value. And in here, we make a bfloat 16 pipeline for add and multiply. And so we need to add and multiply each 16-bit in 4 adder and multiplier. And nothing very special here. And the memory and the write back is almost the same as lab 6. And we need to take a look at the adder and the multiplier. The multiplier is less complex because of the structure of bflow 16. So we divide our multiplier and the adder into 3 stages. So this part is we need to prevent some problem when we do some onboard experiment because the clock is limited, so we cannot do a very long critical path in here. So basically we just do one operation in one stage and pass the result into the second stage, and so we can prove some prevent some problem. And the adder uh, is very complex, but also we change it into a 3-stage pipeline. So we can see it in the top file. In here, we split the EX stage into EX1, EX2, EX3 stage. And the add and the subtract and the ReLU is performed in EX1, and the bflow 16 operation is performed in the 3 stage. And in the EX3 we have a large multiplexer to choose the result and pass it to the memory stage. So now let's take a look at the test bench. Nothing very special. We just check the register value. So we can see the result is all pass, and add a multiply value all pass the test, and the simulation we can see our register. So when the clock start and the register reset become 1, we use several clock to move our data from the memory to register file. And the separate is short, but in here we can find out that in here we have a result of bflow 16. So we use a longer time, but the result is correct. So the simulation is, I think, is pass the test. So I think this is all the information I need to include. Thank you very much.
Ting ting ting. This video is to record a demo for the EE the class EE533 Lab 7, and I'm gonna to record verify our GPU design in the NetFPGA. First, let me connect the service, and we have already uploaded our design build file to the NetFPGA, so I just compare it. Yes, it's our Lab 7 GPU design build file. It is successfully compiled, and let me test it. Wait 3 seconds. Let the system. And now I'm going to compile it. Use our verify script. Okay, you can see that all tests are passed. It shows that our design can work and successfully work on that FPGA. And now let me test the NetFPGA router function to show that our design did not corrupt its router function. Sorry, I forgot. You can see that you can pin the nodes successfully, so that we can our design did not corrupt the router function. It can work successfully. Okay, that's all the verification for our design, GPU design on the NetFPGA. Thank you.